Hello, and welcome to the Daily Stace for today, Wednesday, March 25th, 2020. I'm your host, Gordon Dewis, also known as Keeper of Maps in Discord and Twitch, filling in for Annie, who just moved and is waiting for her internet to be hooked up. Most Mondays through Fridays, our team will be here putting science in your brain. Usually Wednesdays are for Rocket Roundup, and today is no different. Let's get to it, shall we? First up, a Soyuz 2.1B with a frigate upper stage took off from the Baikonur Cosmodrome in Kazakhstan on Saturday, the 21st of March at 17:06 GMT. With the help of Roscosmos providing the facilities and the launch vehicle, Arianespace providing the commercial launch services, and Sweden's RUAG Space providing the multiple satellite dispenser, OneWeb of Tyson's Corner, Virginia, USA, successfully placed 30 more of their broadband communication satellites into low Earth orbit on Saturday night local time. That brings to 74 the total number of OneWeb satellites in orbit, with the goal of completing its initial constellation of 650 satellites by 2021. The Soyuz rocket used for this launch is a far more capable distant cousin of the old Soviet R-7 ICBM, but at liftoff, this rocket's 32 engines once again blazed an impressive trail into the night sky, much as it did not do when Soviet cosmonaut Alexei Leonov hitched a ride to space back in March of 1965, for that flight took place in the early afternoon. It was during that trip that Leonov became the first human being to exit his capsule while in orbit, connected only by a tether to his ship. His adventure in getting back inside the Soyuz capsule is well known, though. Once he exited the capsule, his spacesuit began to slowly inflate in the vacuum of space, to the point that he initially was unable to re-enter the capsule. He was only able to do so after deliberately venting his suit to space in order to deflate enough to fit through the doorway. OneWeb's goal of completing its own project is also in some trouble, however. Like many companies today, OneWeb is looking at large financial hurdles going forward. To date, they've received over $3.4 billion US to finance their operations, much of it from companies like SoftBank, Qualcomm, and Airbus. But these companies are also being hit hard by poor payouts on investments, the recent severe market fluctuations related to the worldwide COVID-19 epidemic, and the various supply and travel problems also associated with the pandemic. More on this later. While OneWeb has almost 2,000 satellites in various stages of design, planning, and production, and several launches planned for just the upcoming months, many of those launches are now on an indefinite hold, and speculation is running rampant that this company may end up declaring bankruptcy before it can sell its services to a single customer.
Reminder, rocket launches are loud.
Rocket launches are loud. Also on Monday, but this time back in the win column, China's space agency successfully launched 3 new military reconnaissance satellites aboard a Long March 2C from LC-3 Xi'an Satellite Launch Center at 3:43 UTC. First, and so far hardest hit by the recent pandemic, China also seems to have reached a point where their mitigation efforts have been balanced with continuing to advance the national spaceflight agenda. This launch was the 3rd by China just this month, and the 6th successful launch of the year so far. Entitled Yaogan 30-06, the mission lifted off from Sichuan province in southwestern China at 11:43 a.m. local time aboard the Long March 2C. This rocket is a 2-stage liquid-fueled vehicle which can loft up to 2,800 kilograms into low Earth orbit, including sun-synchronous orbits. After leaving the Earth's atmosphere, the upper stage successfully placed 3 Earth observation satellites into their planned low Earth orbits, according to Chinese news agencies. These are Yaogan 2 satellites, and the name Yaogan directly translates to remote observing. Intended for dedicated military use, media outlets have stated that before that various governmental and commercial agencies may be able to access the data collected for things like land use, disaster recovery, resource mapping, and so on. The exact instrumentation on each satellite varies, and precise information on any given satellite is, as you might expect, a little difficult to come by. Some are thought to carry synthetic aperture radar in addition to the usual cameras, and others are suspected to have electronic signals intelligence capacity as well, possibly capable of tracking ships via electronic signals detection. At a minimum, they are believed to have ground resolutions of below 1 meter per pixel in various visual and other wavelengths of light. CCTV, an official media outlet in China, announced that only that the 3 new satellites will be used for electromagnetic environment detection and related technological tests. The trio of spacecraft join the Xuanzin 5 constellation, now consisting of 18 satellites in total. The first trio was sent into orbit back in 2017. No word on whether there was damage associated with falling debris. As you may recall, China typically launches from sites well inland, and so their lower stages routinely crash back onto Earth, sometimes on top of buildings and personal property. But we do have a launch video, and warning, this one is even louder than the last one.
3、2、1，点火。
机上光学、雷达监控正常，遥测信号正常。
现在我宣布。
So normally we don't talk about launches that haven't happened yet, but COVID-19 is affecting everyone, including companies that launch things into orbit. New Zealand, for example, is at the highest level of lockdown. This means that Rocket Lab, which launches their Electron rockets from New Zealand, is postponing their March 30th launch that Annie was going to cover. Ironically, the mission is called Don't Stop Me Now. SpaceX, which launched another batch of Starlink satellites last week, had another Falcon 9 launch scheduled for the end of the month from Cape Canaveral. Well, US military officials have said that they remain ready to support such launches, including ULA's Atlas V launch of AEHF-6, which is still scheduled for next Thursday. The travel restrictions in places like the US and Argentina have prevented needed personnel from making the trip, meaning that the SAOCOM 1B mission is now indefinitely postponed. And Astra, who had an anomaly during their pre-launch tests on Monday, said that while it doesn't look like the current coronavirus crisis contributed to any technical issues, it seems very likely that it will impact repairs and the rescheduling of the launch that was supposed to happen today. So to wrap things up, here's a running tally of a few space flight statistics for the year. Total toilets burned up, 1. Total new satellites in orbit, 344, and that includes those that are launched from other in-orbit spacecraft such as the ISS. Total satellites from launches, 330. And Annie keeps track of orbital launches by where they're launched from. So here's that breakdown. In 2020 so far, there's been a total of 21 successful launches and 3 failures. The attempts by country, as you can see from this graph, USA has made 8 launches, China has made 7, French Guiana 2, Russia 2, Kazakhstan 2, New Zealand 1, Japan 1, and Iran 1. And finally, your useless space fact for the week. A Sagan is an approximate unit of measurement which may be applied to a set of discrete objects which numbers no less than 4 billion individuals. Etymologically, billions and billions. S equals at least 2 times 10 to the 9th plus 2 times 10 to the 9th. It honors the late Carl Sagan, a famous scientist and science communicator who was known for, among other things, remarking lyrically upon the vastness of space, saying of our universe, once misjudged to be a fixed sphere of stars encircling the sun and planets, the cosmos is now a ballooning expanse of space populated by billions and billions of galaxies, each containing billions and billions of stars. The term seems to have first appeared in a scientific paper written in 2002 and appearing in the published literature in 2004. And that rounds up our show for today. Thank you all for listening. Today's script was written by Dave Ballard, lightly edited by me, Gordon Dewis. The Daily Space is produced by Susie Murph, and my studio production assistant was none other than the inimitable Dr. Pamela Gay, who was also our fearless leader. This has been a production of the Planetary Science Institute, a 501c3 nonprofit dedicated to exploring our solar system and beyond. We are here thanks to the generous contributions of people like you. If you want to become a supporter of the show, check us out at patreon.com/cosmoquest.x. Now don't go anywhere. In just a few minutes, we're going to have a special treat. Dr. Jonathan McDowell is going to be coming on to talk about Starlink with Pamela. In the meantime, I'll do the best I can answer your questions in chat. If you can just use the purple star, that would be great. I'll do the best I can answer your questions in chat. If you can just use the purple star, that would be great. So I'm just scrolling back through chat here off screen. All right. Well, it looks like you guys are being a quiet bunch today. Are you being nice to me because I'm not Annie? You guys are being all right. Well, thank you all very much, and enjoy our presentation from our guest speaker.
All right. Hello once again, everyone, and welcome to this extra special edition of Rocket Wednesday. I am Dr. Pamela Gay, and I will be your host as we bring an interview to you with the fabulous Dr. Jonathan McDowell, who is a longtime columnist for Sky and Telescope magazine, produces his own space report, keeps up statistics on what's up in the orbits above our heads, and has recently submitted, and I believe has accepted maybe, a paper on Starlink and how they're going to be visible to us. Now, as a reminder, Rocket Wednesdays are normally brought to you by Annie Wilson, who does know much about rockets and especially about space toilets. As she often says about herself and astronomy, I only know enough about rockets to be dangerous. But we have Jonathan here to hopefully keep me on the straight and narrow. So welcome, Jonathan.
It's so nice to see you, Pamela.
It is. Sorry, I had to remember what screen I should be looking at. So can you tell folks a little bit about the crazy combination of skills that you brought to bear in doing this paper on Starlink? Because a lot of people have been going out, looking up and complaining about, well, Starlinks, but sometimes you have to throw stats at things.
Yeah, sometimes you need to do the math.
Yeah.
And so this paper, I feel, is sort of coming together of my two lives. In that, so my day job, as you know, well, I'm an astronomer. I study quasars and black holes. I'm part of the Chandra X-ray Observatory team. And then I have this other life as the historian of the space program. I do the Jonathan Space Report newsletter. And so as I became aware of Starlink, and it became apparent that this was going to be a thing, it seemed like, oh, okay, well, someone really should write this up properly. And eventually the penny dropped that, yeah, it really should be me, because I know about astronomy. I'm a practicing astronomer, and yet I know more about the space stuff than most of my colleagues. And so, as early as last fall, I was wandering around the halls of the CFA, knocking on ground-based observer stores, going, have you heard about this stuff? You
Yeah.
might want to worry about it.
Yeah.
And so I figured it was time to actually, put some numbers on it, see how bad it really might be, because right now there are 360 Starlink satellites launched, and that is, as you said, it's been drawing some attention. But wait till there are 12,000, which is what the approved plan is.
And your paper only looks at Starlink. It's not looking at OneWeb. It's not looking at any of the other constellations. So the reality will be a bit more concerning.
Potentially, and you can use the graphs in my paper to sort of scale for other constellations, and so I think there's information in there that you can kind of scale to what really happens. It's also possible, right, that Starlink won't deploy in the way that they've been approved to do. I hear that maybe, for example, the 1,100 kilometer layer that contributes a lot to the concern for professional astronomers may actually not happen that way. They may fly it lower.
Mm-hmm.
And get if they can get an approval from the FCC and the FAA to do that. And so that's why when I was doing my calculations, I kind of kept separate the contributions from the different altitudes, so that as things change, you can just take the figures in my paper and kind of scale them accordingly.
Now, Starlink is one of these things that is a bit of an ethical conundrum to try and sort out. And this episode, I just want to make clear to everyone out there, we're not going to get into the ethics. That is a different show. Starlink is designed, whether you believe Elon Musk or not, to bring low-cost internet to the entirety of the planet. Do you have any details you want to bring to what is the purpose of Starlink?
Right. I mean, that's basically it. Actually, the real purpose of Starlink is to make Elon enough money so that he can fund his Mars program. I think that's really what's behind it. But yes, the ostensible purpose is cheap internet for everyone, and who doesn't want that?
Right.
Especially right now.
Yes.
And lots of bandwidth. And so because you need lots of bandwidth, you have to have relatively large satellites. CubeSats ain't going to do it.
Mm-hmm.
And they have to be relatively low so that the signal is strong and also the latency is low. That's to say the time that it takes for the signal to get up and down. And so that's what leads them to a large number of big satellites in low orbit. And of course, what we had not appreciated until I started going, that means they're going to be really bright.
And this is that whole 1/r² thing that astronomers deal with on a regular basis. If you have a planet that is at one distance and you put the exact same planet 3 times further away, it's now 9 times fainter. So every time you move something, the amount you move it, square that, and that's how much fainter or brighter it's going to be. So
that's right, which is why, for example, the OneWeb satellites, which are twice as high as the current Starlinks, are 4 times fainter.
Right.
And so so this is one of the things that kind of spurred me to write, particularly the first half of my paper, was when Elon goes, there are 18,000 satellites up there already, so another 20,000, 12,000, whatever, isn't going to change things dramatically. Yeah, but and the trouble is that if you look not just at all tracked objects, including all the debris and blah blah blah, and the bigger satellites that are mostly up in geostationary orbit and so really faint, if you just look at big satellites in low orbit, and by low orbit I mean below 600 kilometers, which we can get into why that's
so International Space Station height objects.
International Space Station height-ish, plus or minus. And so that at that level, before Starlink started launching, there were only about 400 objects that were big and low. And so 12,000 compared to 400 is actually kind of a big change. And so that's, I wanted to get that in the literature and just sort of establish that yeah, you know, we're entering a new era in the use of space.
And to look at those 400 objects, a lot of us in this community, because we love astronomy and spacecraft and all that sort of stuff, actually go outside and occasionally look up and leave our keyboards. And when you see satellites, they're generally among those 400 that are in low Earth orbit. When you go to heavens above and look to see what's visible, you get things like the Hubble Space Telescope, the International Space Station, and other of those 400 objects. These are the things that we purposefully go out to look at. But when there's only 400, you actually have to plan to go outside and see something.
Right. You might be lucky and look up and see one or on a very rare occasion 2 objects going overhead.
Yeah.
You might see, you know, often with there's like a rocket stage from one of those Yaogan Chinese launches that we were just hearing about in the previous segment. So, you know, there's a bunch up there, but you know, the difference between, oh, occasionally you see one and that's kind of cool, to there's a couple hundred up right all the time, I think is quite different. And so I wanted to look into that. And you know, it turns out once you do the math, it wasn't as bad as I had feared. So that's the good news. And in particular at intermediate latitudes, like say the southern United States or Cerro Tololo in Chile, in the winter, you get many hours in the middle of the night where the satellites are not illuminated because the sun's far enough below the horizon. And so that's, you know, astronomy can continue in those circumstances. On the other hand, also the other thing is also a lot of the satellites are going to be sort of near the horizon, and relatively fewer of them are going to be up above, say, 30 degrees latitude.
So let's try and unpack this.
Mm-hmm.
We have essentially a swarm, I'm going to go with swarm, of satellites that are in a variety of orbits to allow everyone to always have some satellites overhead. And so the question we're trying to figure out is, yes, we know there's going to be a bunch overhead, but which ones can we actually see?
Right.
What factors go into figuring out what's visible and what's not? And let's just start by looking at, say, the equator and Canada, so like 45 degrees north latitude.
Right. So the bulk of the Starlink constellation is going to be in orbit around the Earth with an orbital inclination of 53 degrees, which means each satellite goes from 53 south to 53 north and back down again. And if you think about the projection of a circle, an inclined circle, right, what happens, you have this projection effect that's very familiar to astronomers who study, for example, supernova remnants or something like that, where the edges get bright. You know, that the satellites spend a lot of their time at those extremes of latitude. And so if you happen to be living within, you know, 10 degrees of 53, north or south, you see more, about twice as many maybe, as you see if you're at the equator.
Okay.
And so it's just a simple geometry thing. And so that's one factor, is how many are going to be actually overhead at any one time. And even at the equator, it's typically going to be hundreds.
Yeah.
And then we don't, unless you see in the submillimeter, you need them to be, they're only shining by reflected light in the visible, right? And so
let's just explain that submillimeter. That means they're warm, people.
Yeah,
submillimeter is like
the sun shines on them. They absorb the sunlight partly, and they'll glow, but they'll glow in the far infrared,
right?
Right. So that could be an issue for those astronomers who study those wavebands, but I haven't looked into that. Some people have. But they also reflect light.
Yeah.
but they only reflect light if they can see the sun, right? And so the question is the sun above the horizon for the satellite, but not above the horizon for you? If the sun is above the horizon for you, it's daytime, and you probably can't see them, and you don't care because you're astronomers and you don't look up in the daytime unless you're a solar physicist, and then I can't help you. But some of my best friends, I know, never mind. So the satellites are, but the thing is that if you're 500 kilometers up, right, it may be nighttime below you, but still daytime where you are, because you can see the sun over the horizon further. And so that's when we see satellites, when they are high enough up that, and it's short enough after sunset that they're still illuminated, but you're not. And so you do that calculation, and that where the latitude comes in again, because those of us who live at more northern, more extreme latitudes, I grew up in England at 52-ish north, right, where you didn't see it's not quite land of the midnight sun, but it was getting that way, and the winters were sort of rampant seasonal affective disorder. And so you have long nights where the sun is well below the horizon, but then you have in the summer very short nights where the sun you actually never get astronomical twilight. You never get the sun far enough below the horizon for it to be completely dark. And so there you're going to get these satellites illuminated throughout the night. And so those two factors, the orbital geometry and the seasonal geometry of the Earth's tilt, making the summer months short, combine to make these more extreme latitudes in summer good for illuminating low orbit satellites, which is bad if you want to be able to see anything else. And so that's really all, it's as simple as that. And you can do a lot of more calculations about the shape of the satellite and how it reflects in different directions and what we call the phase effect. And so I didn't bother about any of that. I mean, that's a second order thing, right? Because from our observations, which is another piece of the paper we can know about, from the observations, it seems like it doesn't make that much difference, really. That once they get a certain amount above the horizon, they're going to be bright, and they're going to be really bright.
And one way to think about that seasonal effect is if you're on the equator, and this is a super weird and awesome thing to get to experience if you ever travel. When you're on the equator, the sun sets almost straight down. There's some variation, but twilight is very short because the sun is like, I'm fast tracking away from you. I'm just going down. Whereas in the summer, you have the sun it's determined not to go as far beneath your horizon. So it's coming in at a completely different angle if you're in the north, where instead of just sinking and staying there, it's just going to be like, I'm just going to hint below the horizon. And that hinting below the horizon that causes this extremely long twilight in the extreme north and south latitudes. You can stick a whole lot of satellites in the sunlight above head while you're just barely within the shadow of the Earth. And this is a problem. So the longer your twilight, the more satellites you're going to see.
That's right. And, let's be clear. If you are like Elon in Los Angeles, or if you're in a big city, this isn't going to bother you because the satellites are bright, but they're not that bright. They're not as bright as or only in their initial deployment orbits are they as bright as the really bright stars like Betelgeuse or something like that, right? And so it's when you get out into the countryside, and maybe you're going hiking or camping, or maybe you actually live somewhere with dark skies. Then these things, they're going to be fifth magnitude typically, sometimes brighter, sometimes third or fourth. And so then they're going to be noticeable if you have a nice dark sky, and if you have a low horizon, so that it's not built up with either skyscrapers or trees or things like that. Then, so if you're out in the plains in the Midwest, say, or something, or on a boat, you'll see the horizon probably, and then you'll see a lot more of them because they will bunch near the horizon, and so. But even in sort of southern Canada, England, in dark areas, in the summer nights, you could easily see 50 to 100 of these up at once.
And our chat is filled with people from Canada. And everyone in Canada is in southern Canada. Let's just be honest here.
Yeah, well, that's true. Yeah.
And I know we also have England and Montana and South Dakota in the house. So all you folks out there who have suffered through winter with me, you're going to suffer through satellites. But so when I hear you saying they're all going to be hanging out on the horizon, the first thing I think about is, yeah, but when you're using a telescope to do observational astronomy, you're supposed to look straight up, so you're looking through as little atmosphere as possible. But at the American Astronomical Society meeting, everyone was complaining about how these satellites are going to completely ruin all of our survey astronomy, which really, if they're doing it, why wouldn't they be straight? Uncouple these two problems of astronomy should be looking up and the satellites are maximally on the horizon. Can you?
Yeah, sure. Well, first is, I mean, they're not all on the horizon.
Right.
Right. So you can still, in worst case, have 50 to 100, at air mass less than 2 at the overhead. And you can certainly, if you fiddle with the parameters, find situations where, so I have an equation in my paper which kind of goes, on average, how many satellite streaks are you going to have in an astronomical exposure? And it depends on things like the field of view and how long your exposure is. And you can easily get that number to average to something close to 1.
Okay.
Sucks. Almost every exposure will have a streak. So now it may not be let me step back a little. The good news, that is the last couple of weeks' good news, is that we've finally now got observations of DarkSat in its operational orbit.
And this is the one satellite that they painted?
Yes. So of the 360 satellites that they've launched, they gave one a special coating on its nadir side, on its underside, to try and reduce its brightness. And it was launched early in the year, and it spent a couple of months getting up to its final orbit. And during that period, it looked as bright as all the others. And we were like, oh, this isn't looking very encouraging. But at the beginning of March, it reached its operational orbit, did an orientation maneuver to point the dark side down. And it faded by 1 or 2 magnitudes.
Okay. Now, if you're an 8-meter telescope, is that enough to matter?
No, but for some purposes it may. I mean, it may get it. First thing is, if they all, if you eventually, the later generations of Starlinks are all like that, right? It does help you not have them be naked eye objects. And so I am sort of attacking these 2 separate problems, right, as you rightly point out, which are the experience of the night sky for the average person, and the challenge for professional astronomers.
Okay.
And I'm not convinced that this will be enough to fix things for professional astronomers.
Okay. But
it may likely be enough to fix things for the lay persons or the amateur astronomers' visual experience of the night sky. And that's really important without getting into the ethical stuff. As you said, that was off limits, but it's you can imagine countries all over the world that maybe don't have space programs caring that someone has totally changed their night sky. So that is so I applaud SpaceX for putting some engineering into this, and they say they're going to continue working on it. And so that's, so the calculations in my paper were pre that. And so I see them as kind of like the bar for, this is why you have to do something. rather than a prediction of what will actually happen. And so now SpaceX are trying to, come under that bar and improve things, and that's great. Whether they'll do it enough to make 8-meter telescopes be able to make observations when these things are passing overhead, that remains to be seen. But it's early days yet.
And the reason this gets to be annoying to problematic is when you're observing and a satellite goes through your image, you can't measure the brightness of anything underneath that satellite streak. And if it is a particularly bright satellite, our digital detectors are like, holy expletive Batman, I'm not going to be happy until I have flushed my sensor 2 or 3 times. So you can end up with ghost effects from particularly bright satellites. Now, I've been lucky. The telescopes that I've personally used have either been small with a huge field of view to go searching for galaxy clusters and study variable stars and small galaxies, or they have been massive telescopes with a little tiny field of view where I was studying the things that I had found with the smaller telescope, but in greater detail. And while I regularly saw satellites on the giant field of view, it was a little over a degree, my 6-minute field of view, my 6 arc minute wide field of view, I can't remember a single satellite I captured with that. Now, when you have at least one satellite in every single image, that means you have to throw out that chunk of the image and just keep taking multiple images, slowing how long it takes you to get the necessary data. A lot of us astronomers do what's called min-max rejection. This is where you take a whole bunch of images of the same field and you stack them together after saying these pixels are statistically way brighter than they should be. So we're going to assume they got hit with a cosmic ray, an airplane, a satellite. You don't actually hit the pixel with the satellite, but the light. And the minimum ones, just sometimes things happen. You need a whole lot more images to stack things together to get the needed signal if you need to throw out more data.
That's right. And so you can do these min-max, you can do medium filtering. There are various mitigations that basically increase the cost of doing business. They increase the amount of observing time you need, which, given the fact that you also need good weather and stuff like that, there's only a certain number of hours in and a particular object you're looking at, right, may only be visible for a month as the Earth goes around the sun. And so, there's going to be science you can't do if it takes 3 times as long to do everything. And that mitigation only works as long as the average number of satellite streaks per image is at most a couple.
Yeah.
Right? If you get to the point where you've got like 10 satellite streaks per image, then a lot of these mitigations stop working because you get multiple pixels hit and you can no longer tell what's good and what's bad. And I think we're not in that situation with Starlink.
Right.
But I see this as just the first step in a new industrial revolution in space.
Yeah.
It's going to change the character of low Earth orbit. And so I think unless we do something regulatory to cap the number of large, bright satellites in low orbit, we will eventually get to the point where these mitigations don't work. Another mitigation you can imagine doing, right, is if you, next to your big telescope, have a little telescope with a wider field of view.
Yes.
That then can spot a satellite that's about to enter the field of view of the big one, trigger a shutter, and so on. And so as long as most of the time there isn't a satellite crossing your field of view, you can do tricks like that.
Yeah.
It's expensive to set up, but doable, right? But again, as when you get to the point where there's always a satellite going over, then that doesn't work either.
And crazy mitigations that are being imagined are things like currently, when you're scheduling your observing run, at least the way I always did it was I basically figured out with all the objects I was looking at, okay, when are they about to cross the highest point in the sky they're going to get to, and how can I arrange it so that I'm essentially trying to observe each of them as they clock through their highest point. And there's other things you have to consider, like standard fields, so that you can go from an unknown object on the sky to something that you know how bright it is, to do calibrations. And it's trickstery, but basically all you're worried about is when are things where. Straightforward. Well, now you also, in theory, will eventually be able to use software to figure out when these satellites will be able to cross your field of view. And it will require constant updates because these things are on the move. But Elon Musk and his team have said they're going to put all of this information into publicly accessible databases so that you can always know this one's about to go through my field. And so suddenly it becomes a matter of optimizing, not just when do you observe based on where in the sky, but also based on when are you going to get flooded with Starlinks. And so suddenly you're playing a video game where you're bouncing back and forth between objects that have no Starlinks in front of them. So instead of just sitting on your object,
just making astronomy more fun.
Well, it makes it more fun. At a certain point, I have a terrible desire to write a grant to write the observing software to do this, but I'm also...
Well, I think there's a problem with this, though,
Yeah.
which is that, Elon said, I mean, they have these things called supplemental TLEs that they make available on a website that you can get now to say, where is each of the Starlink satellites. But they're all maneuvering. Potentially, they're maneuvering to avoid each other. And so with sufficient number of satellites, once the full constellation is deployed, satellite A will maneuver to avoid satellite B, which will trigger satellite C to avoid satellite A. And I suspect that the freshness of the orbital data will be insufficient for us to play this game. And so I don't think we can rely on that. I think we're actually going to have to do more what I said of I actually see him coming and dodge.
That makes me sad.
And because I think that in general, SpaceX have made very confident statements about the space traffic management aspects of their constellation and how they're going to be able to avoid avoid collision dangers and things like that. And I think it's going to end up, I think the tracking is not as good as they think.
Okay.
And the error rate is too high. I mean, it takes, especially when new constellations, new batches are launched, it's taking a couple of weeks right now for the 60 satellites to be identified and tracked properly, right? To sort through the confusion. And maybe it's worth sort of going through that in a little more detail, that how do you track a satellite, right? So you launch them, they come over your tracking station, there's 60 of them come over your tracking station. An hour and a half later, you see 60 or maybe 58 or 62 come over your tracking station. Now the question is, which one, satellite 30 in the first batch, which one is it in the second batch? And so you've got an n squared problem there, trying to match this, and you've got to do that every orbit. And so until you get the errors down well enough to be able to accurately predict from the orbit which one it is that comes over next. And so they're all very close together. There are uncertainties. It's very hard. It's very easy to mistag, to mispair two observations and get an orbit that's spurious.
And Musk isn't doing all this high-level tracking, and these things don't have responders on them the way aircraft do. It's not like you can just look at your thing and tell by responder which is which.
Musk can actually, because they have telemetry from the satellites. And the satellite ID of the telemetry, so that helps them get the right answer. But the Air Force don't do that. They just
that's what I meant. Yeah, the Air Force can't look at the transponders.
And so when you're so you either have to rely on what SpaceX feeds, which, again, there's a communication issue potentially. And if there's 20 different operators, that gets complicated. Or you have to rely on the skin tracking, the radar tracking, and then that takes weeks to sort out, and the system's already overwhelmed. Never mind what it's going to be like with 12,000. So that's one thing. I wanted to go back to what you said about the narrow field of view, and that never having seen a satellite that way. I was in that mode too until a week or so ago, when I think it was Judy Schmidt sent me on Twitter an image that she just taken with Hubble. Hubble's a classic case of a narrow field of view where you don't expect to have problem with satellite trails. And she was looking at a cluster of galaxies for like lensing arcs or something, right? And there's this big fat satellite trail right through the cluster of galaxies at target, just ruining the Hubble image. And Hubble's 600 kilometers up, but it turns out that a Chinese rocket stage, this is a fun investigation that I did, what the heck could this be? An old Chinese rocket stage passed just 35 kilometers above Hubble, right in the direction that Hubble was looking.
Oh, geez.
And so this is actually the satellite track here is resolved. It's like 12 arc seconds across or something.
And Hubble doesn't care. You don't get to make up those orbits. That's your data toasted. Yeah.
And so, again, it's unlikely, right? This was a one in many rare occurrence at the moment. But once you have thousands of satellites in these higher 1,100 kilometer orbits, right? Starlink's first layer is below Hubble, but this other layer, the OneWeb, is above Hubble. And so it's not just ground-based telescopes that are going to have to worry about this. So I think it's going to be, and again, I haven't run the numbers to see just how massively unlikely this was. But the fact that it can happen at all says, okay, yeah, we probably better worry about it.
Yeah. So we're getting a whole bunch of questions coming in on the chat. So I'm gonna start with Roadster Tracker has a whole bunch of related questions, just basically trying to do the okay. So I'm a spacecraft person trying to understand the effects on astronomy set of questions. So the first place to start is for astronomy. What parts of the night do we want? And my generic answer is if the sun is down so that we have no more astronomical twilight, that time of night is gold. And during that time of night, do we need to worry about I have darkness, satellites don't, death by Starlink?
Yeah, I mean, it varies, right? So like I was saying, when you have the full astronomical twilight, the satellites tend not to be illuminated in the lower orbits. They are in the higher orbits, though. So even the 1,100 kilometer layer is going to be illuminated even after astronomical twilight because it's high enough it can still see the sun. Like I was saying, when the sun is really way below the horizon, in the middle of winter, in the midnight, then yeah, you've got no problem, but or less problem, I should say.
But there's a lot of objects out there that are never going to be high in the sky at midnight in winter.
Right, that's true. So the other problem though is there is some gold science that gets done in astronomical twilight.
Yes.
And for the non-astronomers listening, when an astronomer says astronomical twilight, they mean what you mean by night. Right? It's not like, oh, it's pretty out, and it's like, no, it's dark. It's just not super dark. So that you can do the pushing the edge astronomy. But if, for example, you are looking for near Earth objects that are close to the sun in their orbits, and therefore the sun, you have to look near the sun, which means not long after sunset, or not long before dawn, then you are superhosed by Starlink. And a lot of us feel like near Earth object surveys might be actually kind of important
Yeah, we like our planet most of the time.
So I think that's the one, and they also require wide field of view and long exposures
Right.
to find, you know,
Faint,
faint things.
small, deadly objects.
And so it's sort of a perfect storm of all the things that make Starlink bad for you. And so that is a science use case that I worry about. And I think, just to say here, astronomy is very heterogeneous in the sense that every astronomer does a different kind of observation,
Yeah.
with different kinds of instruments, and so they are affected to different amounts.
Yeah.
And there's astronomy that's really not going to care too much.
Right.
I think if you're doing fiber spectroscopy, you might get hosed, but if a satellite happens
Statistically.
to go over your fiber, then that whole observation is going to get
Yeah.
hosed. You're less likely for that to happen. So there are and Starlink affects you in different ways. If you're doing light curves, you might be more worried about an occultation by a satellite, even if it isn't illuminated. Now the satellite's very fast, and so it's a very brief flicker. But not many people are looking for millisecond eclipses. But still, things like that you might have to worry about. So it varies a lot, but yeah, in the middle of the night, you're probably okay. But there's a few hours of good astronomy, professional astronomy time on either side of the middle of the night, where you still get illuminated satellites, and it's still an issue.
Yeah, and Roadster Tracker points out that SpaceX can send their data to CSPOC and they can feed that information directly into the system. Do you know if SpaceX is sending out any of their telemetry data just on an open?
It's not directly telemetry data, but they do orbital solutions, and then they do send them to the 18 SPCS, the 18th Space Control Squadron.
Okay.
And they didn't used to, but they've started doing that now. Whether the 18 SPCS is successfully integrating that, because historically they haven't been really set up to take information from outside. No, it's not their thing. But I think those barriers are coming down now, and it will improve. And so yeah, in principle that can happen. But it doesn't seem to, like, it's still the case, right, that the most recent launch, I don't think they've made the matches yet.
Okay.
So it's faster than it was, but it's still taking some time. And there are still plenty of cases where I have to look at the orbital elements and go, oh, that one got mistagged. That's a bogus orbit. So even in the ones that have been up for a while. And so you can't assume that the processes and algorithms are infallible.
Yeah.
Right? There's some error rate always, and it's actually higher than you might think. And so there's yeah, for the most part they're getting better. But you can tell that it's stressing the system with this many satellites, and we're only at the beginning.
And one of the ways that this feels to me is I've been doing observational astronomy since I was like old enough to calculus. And when I first started, there was a one and only one 6-meter telescope in the world, and that was the 6-meter in the Soviet Union. There were a bunch of like 1-meter telescopes, and those were like, oh my God, it's 1 meter. And over the years, as we've tried to do harder and harder science, we have begun to get to the point where a 4 meter is a throwaway telescope. It's the 8 meters we need. And it would be really easy to say that we're still going to be able to do all of our 8-meter science, but at a rate like we did it with the 1-meter telescopes when it comes to gathering light. So all we're doing is setting back our speed that we acquire data to where it was in the 90s, because you're just going to have to sit there longer to not deal with satellites. And we did science in the 90s. We did science in the 80s. It's not that bad, astronomers. But the thing is, we've solved those problems. And so can you have a longer perspective than I do, even though I go back to the 90s.
Yeah. So no, that's right. I mean, I remember using 4 meters, back in the 80s in grad school.
Yeah.
But yeah, I think one thing people don't appreciate is how many professional telescopes there are in the world.
Yeah.
There, as you say, there's a few like 10 meters and 8 meters and a bunch of 4 meters, and like I don't know how many 1-meter professional telescopes there are in the world.
They're starting to throw them out. There's so many.
And I mean, it must be hundreds, and the total number of professional telescopes must be in the thousands, I would think. And the thing is that there's great science being done in those telescopes, particularly with exoplanets and stuff like that. Things like, how big was the 2-mass telescope? It was
those are 1-meter class telescopes, and the HARPS spectrograph is on one of these 1-meter class.
Right. So it's we're still using these smaller telescopes, many of them doing many different projects, and that's why if every professional telescope has to be re-equipped with some like anti-Starlink magic, that's going to be super expensive. And that's also why you can't just say put everything in space, right? Because it's not just, let's put these 5 big telescopes in space. No, it's like put these 1,000 small ones in space. Even with Elon giving free rides, that a space telescope is not cheap to build. And so there's this whole range, and they're all going to be impacted at some level or other. And we're going to have to sort of change the designs on our cameras, and an astronomical camera can easily cost $1 million,
right?
Even without Starlink modifications, right? So
well, and the giant spectrographs, this is something that no one ever talks about. We have facilities that the instrument alone will weigh 600 tons.
Right.
Because it's spread out over essentially the entire basement of a 8-meter telescope's dome.
Very true.
And you can't launch these. And there's also the fact that we don't always know if our instruments are going to work when we're trying, and it's good to be able to send a graduate student up the mountain to fiddle with the bits.
Yeah, no, there's also that the thing that makes ground-based telescopes cheaper, right, is that you don't have the remote control ability to fiddle with the bits.
Yes.
Because you can send the grad student there.
Yes.
And so and you can clean it every year, down for a week in the summer.
Every week. So I'm sorry, but my data, we cleaned those filters every single night.
I'm talking about the mirror realism.
Oh, that's true. Yeah. You resilver mirrors and things like that.
Yeah. So, but you're right. No, there's all kinds of things that you do hands-on. That you would have to automate and therefore make much more expensive for space. So yeah, you're right at the big end. You're basically turning an 8-meter telescope into a 5-meter one or something like that. Yeah. But like I said, it's not clear the math works that simply to me.
Yeah.
I mean, overall, it's just more observing time, and therefore less projects get done. So astronomy is slower. Maybe that's for free internet for everyone or cheap internet for everyone, and making Elon rich. That's worth doing. What is the hit? But I'm more worried about projects that just get to be undoable and impractical if you have too much of an observing time hit. and or if you can't get a dark enough sky or things like that. So and I think, one of the things that worries me is, the thing that surprised me when I went to the AAS, Tony Tyson talking about the bleed out effects on the electronics from a bright satellite passing over. If the satellite is bright enough, having all these spurious, basically crapping out the instrument, right? Due to electronic stuff, which is magic that I don't understand. So I hadn't anticipated that. And I wonder to what extent we're going to see unexpected problems due to what happens when lots of really bright satellites pass over your instrument, because we just haven't had that many up until now, and so we're not as familiar with we're going to be surprised by what challenges we face. That's the concern I have there. So we'll find out. I guess maybe it won't be as bad as we fear, and certainly I've tried in this paper to bound it so that there are going to be times when it's not as big of an impact. But and really my message is that it's within an order of magnitude of being really bad, and therefore whether or not Starlink is a problem, we have to think about regulating this in the long term.
And what kinds of regulations would you love to see? There's actually a UN office, for those of you who aren't aware, there's a UN office that tries to put out international agreements on stuff like this. It's located in Vienna, Austria. If you could go to the FAA, if you could go to the UN relevant offices, what guidelines would you want to put out?
Right. Well, I think what's been done for orbital debris is a good model. And so there's a couple of avenues. One is so that the United Nations COPUOS, the Committee on the Peaceful Uses of Outer Space, and their Office of Outer Space Affairs, which just parenthetically, I have a business card from one of those folks, right? This is like United Nations Office of Outer Space Affairs. Can I see your alien registration card, please? I kind of want that job, except it would be so horrible dealing with bureaucracy.
Yes, the bureaucracy, no. The business card,
just
yes.
The business card, yeah.
I'd be willing to be their IT person.
Right, exactly. And so they have put out a what are called space sustainability guidelines, which are a bunch of kind of motherhood statements about how we make space, how we use space in a way that will be sustainable, that don't really have any force, but then can be used by individual countries to set more specific policies. And because international treaties and agreements are so last century, that the best we can hope for now is the sort of general kind of wouldn't it be nice statements at the international level, and hoping that the individual governments pick them up. And that has worked for debris. There's also a thing called the IADC, the Interagency Debris Committee, which is not a UN body. It's the engineers from the various space agencies getting together.
This is COSPAR, isn't it?
I think they may have an affiliation with COSPAR, but it was NASA and Roscosmos and the Japanese agency and ESA.
JAXA, ESA, and
getting together and forming a committee of their experts, issuing recommendations that then they could take back to their various agencies and go, this is what we think our internal policies should be. And so basically, cutting out the UN level and working at the engineer level, country to country, to go, let's at least recommend policies that we can agree on to our respective governments. And that's been taken up pretty well in terms of things like the 25-year rule for satellites should re-enter in low orbit within 25 years of when you turn them off. And the geostationary graveyard, which is up in the geostationary orbit where it's too high to bring them back down, push them up at least 300 kilometers, and then maybe they won't
interfere.
Geo. And so that is a path that we could go with light pollution. we could say the night sky is part of the heritage of humanity, and users of space are encouraged not to totally screw up the night sky. And that then something, a body like the IDC could come up with recommendations for no single constellation should have more than X satellites above Y brightness.
Okay.
And also, I think there's going to have to be a cap on the number of satellites in low orbit, just from traffic point of view. And we can fold light pollution concerns into that discussion. So I think there are ways forward. And I think, unfortunately, the astronomy community sort of dropped the ball. We should have been doing this 10 years ago. We should have seen it coming, and we didn't. And so now we have to engage with these space governance bodies that we have not had relationships with in the past, for the most part, except the radio astronomers who, you know, have worried about satellite interference.
Yeah, and commercial space, dealing with it is so different because it's not limited in speed by the power of bureaucracy. You and I have both dealt with NASA enough to know that anything that you want to do quickly, you will not. And it's simply because there is so much paperwork, committee meetings about having meetings to have meetings, that it gives people this breath to realize, oh, shoot, don't do that. But with commercial space, they don't have that built-in slowdown that you deal with governmental space. And that also means that if we're worried about NASA doing something like this, now would be when to start worrying because of that ramp-up time. Whereas with commercial space that I don't think any of us saw coming the way it did 10 years ago was when to start worrying.
This is true for governance of space in general. The speed of the regulatory bodies is much slower. You know, in astronomy, right, we're always comparing timescales, right?
Yeah.
The timescale for regulatory bodies is much longer than the timescale for this new space industrial revolution. And so that's the fundamental problem. And it's not just affecting astronomers, it's affecting all aspects of governance of space, that things are changing really quickly, and the governance is not keeping up.
Yeah. It's going to be a weird time forward. And there's this is so much more complicated of an issue than we're just hitting on the technical issues. It also becomes so there is no other way to get internet to random islands scattered about the planet. There's no other way to get internet to random parts of Canada. And so how do we balance the economic benefits versus the cultural benefits versus the science benefits? And it is really an ethical issue involving culture, science, and economics. And
but let me just say, I think there is a way forward. I mean, I think there can be a balance. I don't think astronomers are saying, oh, shoot Starlink out of the sky. Well, a few, let's ban Starlink entirely. Let's ban all of these mega constellations. I don't think that's the discussion. The discussion is, how can we balance these competing requirements, and how can we regulate it so that there's at least a discussion before one company decides to do something that changes the environment?
Right.
And I think that I'm optimistic that in the long run, we will evolve to a regime where those discussions are had, and the resources in space are managed in a way that is never going to be perfect, but you know, it sort of lets us get along. And it's just a question of how long it's going to take us to get to that point, and it might be longer than we'd like. And astronomy may have a problem for the next 5 to 10 years while the governance catches up. And the good news is that these satellites, right, are meant to be replaced on a 5-10 year time scale. And so, if you can get the governance in place for 10 years from now, by 15 years from now, that'll all be, what's up there now will have gone. And so there is a recovery timescale, but we were slow off the mark, and so we're going to have a rough time for a bit, I think.
And one thing that just occurred to me for the first time, thank you, Andy Fall, for the follow. You pointed out quite accurately that we've got thousands of telescopes here on the planet, which means that if we did launch all the telescopes into space, they'd be light pollution.
Yep. Well, it depends. Not if you put them all at L2.
You can't put that many telescopes at L2.
Do you know how big L2 is?
Apparently not.
L2 is
and define L2 for everyone. Just
So L2 it's 1 million miles towards midnight. It's a balance point where the gravity of the Earth and the Sun tugging on the satellite are such that the satellite stays on that Earth-Sun line.
Yeah.
And so it's a really nice place to have telescopes because the Sun and the Earth are both behind you.
Right.
So it's like the darkest sky you could want. And it's sort of, you only need a tiny amount of propellant to stay there. But what you do is you don't position your telescope right at L2. You position it in an orbit that's with a radius of about 300,000 kilometers.
Okay.
Like the orbit of the moon around the Earth, around L2.
That's way bigger than I thought.
Yeah, exactly. So very few people realize this. So the space that counts as L2 is actually about as big as the space between the Earth and the moon.
Okay.
And so you can fit a lot of astronomy satellites in that volume without
you can,
worrying.
But wow, we would need to build much bigger receiving stations because the antenna that we use to get data from Hubble it would easily fit in a room. Whereas if you stick everything out that far, you're going to need bigger antennas.
Yeah, well, but it's been done for Herschel, for Planck, for Gaia,
Spitzer.
Right? Spitzer even further out.
Yeah.
So I mean, their data rates are low compared to Hubble, but that's a solvable problem, I think. So in the long run, I think that's where we're headed. I think in the long run, like 100 years from now, there'll be so much activity in low Earth orbit that it will be hard to do astronomy from the ground, and we will have most of our assets out somewhere like L2. But
the best idea just came in on the chat. I love this. So Bill Nash, who is an amazing photographer and also an engineer, he wrote, would it make sense to build a large framework there with a common power and data bus to mount equipment to instead of an orbiting multiple things? And I'm now envisioning like the smallest ever Dyson ring, but instead of putting it around the sun, you put it around L2 and just cover it in telescopes.
Yeah. I actually think that's not the best idea.
No, it's not. But so it's the best in terms of I want this science fiction
the best
show.
Science fiction-y idea. Yes, absolutely. Well, that's I mean, that wasn't that the Argus array was that Star Trek? I can't remember.
Yeah, something like that.
Or maybe it was Contact. Anyway, the trouble is that if you aggregate everything into one system, that tends to mean you have single point failures.
Yeah.
And I think it's actually ends up being cheaper in the long run to have many small things than one big thing. That's the whole point of the CubeSat revolution. Right?
And this is the difference between reality and really awesome special effects.
Right, exactly. And there's arguments for both, right? So I understand how you go through that engineering trade, right? Because, why have, separate power supplies for each spacecraft? You're just duplicating work there. But I think the overhead of coordinating everything and everyone wants to look in different directions, and the environmental conditions for a cryogenic infrared telescope and for a UV telescope, which requires absolutely no contamination, but doesn't care about the temperature as much. All of these things mean you'd actually rather have them far apart from each other, I think. And it's going to end up being cheaper in the end. And where you can win is by common software, common operating systems, common communications platform design, right? So they all have the same power supply and the same solar panels and things like that, but not aggregating them into one Battlestar Galactica spacecraft.
All right, that is all fabulous. I'm switching. I realized I left dog cam up for an obscene amount of time. So I think we could probably talk all day about this, but I unfortunately have science I should be working on.
But whether I'm going to do it or not is a different matter.
Well, it's true. It's true. I sadly need those billable hours to put down.
Yeah. I hear you.
So if people want to keep up with all the various things that you're doing, from Chandra to tracking satellites to random merblings on the internet, where are the best places for people to find you?
Right. Well, so I hang out on Twitter a lot at Planet4589, and I have a website, which the planet4589.org, or you can Google Jonathan Space Report. And so my newsletter's on that website. I cut an issue about once a month, but I update the latest stop press page all the time. And so that covers space launches and stuff like that. And there's also a lot of my science on the website if you dig hard enough in the nav bar. So those are the best places to find me.
And I'm hoping that we can have you back in the future to talk about this evolving problem as you write more papers and do more awesome things to, well, help us figure out just how good our sky is and isn't in this changing future.
I think there's a lot of space topics that we could get into.
Oh, it's true. It's true. And I don't know if you noticed. Sorry, I'm looking at my settings screen is way over there, and my settings box stopped working. So I'm having to look way over there. Okay. So we're definitely going to invite you back. And I just want to say that our audience was super pleased to have you here. And I saw several people like, oh my goodness, I love to watch astronomers talk with their hands, and he's cool. And
oh, thanks.
So
well, it's always a pleasure to see you, Pamela, and stay safe.
Yes.
And I haven't left the house in like 4 days.
I last left the house February 28th. So.
Oh, wow.
Yeah, immunocompromised. I'm not leaving. I'm good.
Yeah, I've got health issues too, and so yeah, I'm going to the grocery store once a week with gloves on.
See, we have a graduate student who's crashing in our spare bedroom, who's being sent as tribute to the grocery store. So,
okay.
He gets free room and board. No, I mean, be honest, it's we get pretty much everything via Instacart. And if there's oh shoot, we need blah, the graduate student does get sent out. He's not my graduate student. He's somebody else's graduate student who's living in my spare bedroom.
Okay, that's all right then.
Yeah, no. There's no ethical grading dilemmas. No, he is somebody else's graduate student who's living in our spare bedroom. Sure. These are things that happen in graduate school. It's normal. I actually lived with a planetary scientist for a little while in graduate school. All right. So thank you for being here, Jonathan. Do stay safe. You are in a big, crowded city in a gorgeous building with amazing windows. So I know at least you're going to get sunlight. Yeah,
you can come visit once this is all over.
I hope so too. It's my hometown. I love it there and miss it. All right, so I'm going to let you go and wrap this up. So I am transitioning you away. If you have any final words, say them now.
Well, keep looking up. This is a great time to be doing astronomy because, there's not much else to do. So thanks for having me, Pamela. Okay, keep up the great work.
I will. So thank you so much for being here, Jonathan. And to everyone else, you're off screen, by the way, to everyone else out there, thank you for sticking around for this special edition of the Daily Space where we took you through. Thank you, Rigel, for the sub. Thank you, Raising, for the follow. Let me bring Doug Cam back up. And for those of you who don't know, we say thank you with cuteness around here. So I just need to figure out how to not cut my head off with Dog Cam. I'm not going to worry about it. I'm going to instead cut off chat with Dog Cam. There we go. That was not apparently the right thing to move. Temporary chaos ensues. All right. So there is a bigger Dog Cam. There we go. Thank you, everyone, for everything that you do to support us here at CosmoQuest. My name is Dr. Pamela Gay, and I have been the host of this second half of the Daily Space with our interview of Dr. Jonathan McDowell. You can check out all of his content, adding the information to the chat, on planet4589.org and find him on Twitter with the same username. This is going to wrap up our coverage for today. I would like to give a very special thanks to our guest host for Rocket Wednesday, Keeper of Maps, Gordon Dewey, and to our instro, our own David Ballard, who wrote that episode. We are here thanks to you. And every day we are finding more ways for you to help us as volunteers who help keep the science flowing. We are here thanks to the generous contributions of people like you. And while we do really like your money, it really does help me pay Susie and Annie, who do like to eat. We know that these are crazy times, and we are here to support all of you through these crazy times. And if you don't have any money to give, that's fine. Come hang out. Play Ticket to Ride with us in the evenings. We're good. If you have extra hours and are bored at your keyboard, go to Discord and visit the Volunteers Reporting for Duty channel, and we will find you ways to help us out. Thank you. Thank you, all the amazing volunteers. I'm going to have to go get my Cheerios box. I am almost out of... Wow, I'm throwing Cheerios at myself. I am almost out. I don't know where that Cheerios... Oh, I threw it off the light. That's where it came from. We have more Cheerios now. The dogs are very happy. Thank you all so much. Thank you, Mythtown, for this sub. Thank you, Astro YYZ. Thank you, Fenmill. Thank you all for helping us keep on keeping on. You are awesome and amazing. But I do need to go make the science flow. So I am going to gear up to start the credits in just a moment. And while I put that together, I'm going to remind all of you that the Daily Space is a production of the Planetary Science Institute, a 501c3 nonprofit dedicated to exploring our solar system and beyond. This episode will be produced by the ever fabulous Susie Murph. And we're here thanks to you, thanks to your volunteer efforts, thanks to your help, thanks to your support, financial, and just by showing up. The best way that you can help us is twofold. You can, go to patreon.com/CosmoQuestX and help us with $1 or more. Or you can just show up on Discord in the Volunteers Reporting for Duty channel and say, I'm here to help. Okay, that's it. Wherever you are in the world, have a fabulous morning, evening, or afternoon. Take care of yourself. Be well, be healthy, stay home, and wash your hands. I'll see you on the other side. Bye-bye.